So in this second half of redox reactions A in this next video, we talked about assigning oxidation numbers. Now we're going to talk about balancing redox reactions in both acidic and basic conditions. So let me give you an example of a redox reaction that's pretty straightforward. This is one of those examples where this is copper, not calcium, plus AgNO3. That's aqueous. And we could balance this just by doing the mass balancing. So 2 silvers, that's solid, and copper, 2 nitrate. Okay. So this is a balanced chemical equation, and because all these things are neutral compounds the way they're written, this is also, so we have 2 silvers, 2 silvers, 2 nitrates, 2 nitrates, because of the 2 out front, 2 coppers. Everything's balanced. I'm sorry, a copper on each side. This is a balanced reaction. Sometimes we'll see these written like this, though, where you have copper solid and silver plus 1, aqueous, going to silver solid plus copper plus 2, aqueous. And in this case, this isn't a balanced reaction because even though the masses are balanced, we have a silver on both sides, we have a copper on both sides. If you look, this is a plus 1 charge, this is a plus 2 charge. And so this is what we call not charge balanced. And so the way we charge balance this is we could put a 2 here and a 2 here. And now 2 times plus 1, this side is overall plus 2. And this side is all overall plus 2. So we now have a balanced redox reaction. So, and oftentimes we don't put these counter ions in there. And so you can see pretty clearly from the bottom one where you take out the nitrates that the copper went from a 0 to a plus 2, so it lost 2 electrons. And this silver went from silver plus 1 to silver 0. Remember, these are neutral. This gained 1 electron, but since there are 2 of them, your number of electrons are balanced. So one of the things we learn how to do in chemistry, in electrochemistry, is break reactions into what are called half reactions. So a half reaction represents either an oxidation or reduction. So we call them half reactions. And they represent either an oxidation or a reduction. And obviously, you can't have a half reaction alone. Ultimately, for a half reaction to occur, you have to have both an oxidation and a reduction, and they come together. We add them together to make a complete reaction. So if we take an oxidation plus a reduction, we make an overall reaction. Okay? So I'm going to show you how to balance half reactions and then ultimately how to balance overall reactions. And the one we just did, you might not have followed, but I'm going to show you how it's a little easier if you think about it. So if we took just a simple reaction like that copper solid plus a silver plus 1 going to silver solid plus copper plus 2 aqueous, this is not a balanced equation, but we could break it into copper going to copper plus 2, which is a half reaction, and silver going plus 1 going to silver solid. I can put aqueous on these. Now, if you say, how do you know which goes where? Well, you couldn't balance these mass-wise if you didn't have a copper here and a copper here. So you can't make copper into silver. So you have to keep the atoms that are the same in the same half reaction. Now, mass-wise, these are already balanced. There's a copper on this side and copper on this side, and here is a silver and a silver. But charge-wise, this is neutral and this is plus 2, so we actually balance charges by adding electrons to the more positive side. So notice this side was plus 2, this side, and I'll write this out in rules. This side is 0. Now, with the plus 2 and the minus 2, it's overall 0. So over here, this side's 0, this side's +1, so I had 1 electron, and now this side, this is a balanced half reaction. So if you look, whenever you have electrons in the products, this is actually an oxidation half reaction. And when you have electrons in the reactants, that's a reduction. Because electrons are being added to whatever here, they're being removed from this particular one. Okay? Now, obviously, when you add these two together, you would have to make sure your electrons cancel. Overall reactions can't have electrons in them. So in order for the electrons to transfer, we have to multiply this whole thing by 2, and this makes 2 electrons. We put a 2 here and a 2 here. That way our overall reaction is going to be copper solid plus 2 Ag plus 1 aqueous going to copper plus 2 aqueous plus 2 silver solids. And this is the overall reaction. Okay? And I know that you might not want to hear this, but this is a more simple example of something where we're going to get more complex here. But here we can pretty much just charge and mass balance and we're done. But a lot of redox reactions interact with the solvent. And so I'm going to give you a set of rules to do this, and then I'll write some examples down that you can actually try afterwards. Okay, so that's where we're headed. So let me give you the rules for balancing half reactions. Okay, so rules for balancing, redox reactions, which will be half reactions as well. And we're going to start under acidic conditions. And if you say, well, why does it matter? Well, a lot of these reactions are aqueous, and if you think of batteries that you've ever used before, because ultimately in this section after this exam, we're going to talk about batteries, and you've probably heard of alkaline or acid batteries. That's because a lot of these reactions are influenced by the pH of the solution. Okay, so balancing redox reactions. The first thing I want you to do is I want you to divide the reaction into 2 unbalanced half reactions. All right. So we should probably do this with a problem as we're going about. So I'm going to, on the next page, I'm going to start one. So let's say I'm going to put a reaction out like this. MnO4 plus C2O4 minus 2 going to Mn plus 2 plus CO2. Okay, and I'm not going to put the phases in right now. If they're ions, they'd be aqueous, and this is a gas. But we'd have counter ions, but typically you pull all the counter ions out, like the potassium permanganate and maybe the sodium oxalate or something. We'd pull, or the Mn nitrate, we'd pull those out so that we don't get confused by them. So if I'm going to split these into 2 half reactions that are unbalanced, we have to pick the things other than oxygen and hydrogen, because we're going to add oxygens and hydrogens. So I'm going to put MnO4 minus 1 going to Mn plus 2, because I know that's what is changing oxidation numbers, and then C2O4 minus 2 going to CO2. Again, if that's tricky for you, look at all atoms other than oxygens and hydrogens and go, I can balance this if the Mn's here and there's an Mn here. I couldn't if I went from Mn to CO2. You can't make atoms different atoms. Okay, so that's the first rule. The second rule is balance the half reactions. And we're going to do this independently from one another. Now, there are 4 rules for doing this. The first thing you do is you balance all atoms other than oxygen and hydrogen. Okay, let's do that. So, in this case, Mn's balanced. There's an Mn there. 2 carbons, so I need a 2 here. Remember, we still balance according to the rules we learned in general chemistry. So I did the first thing. The second thing is you are going to balance oxygen by adding water to the deficient side. So the side that's low on oxygens, we're going to add water. So look, 4 oxygens here, none on this side, so I'm going to put 4 waters on this side. All right? 4 oxygens on this. 2 times 2 is 4. Everything's good. I'm going to skip that step for this particular half reaction. C, you're going to balance H by adding H plus to the deficient side. So remember, H plus is really H3O plus. We kind of make it simpler just so we don't have to worry about it. It's a little more complex. So so there are 8 hydrogens here, so I'm going to put 8 H pluses on this side. No hydrogens on this half reaction, none on this half reaction. I'm done. I like that one. Last thing for balancing half reactions, D, is, if we've done it right so far, everything's balanced except, everything is balanced mass-wise. All our other atoms, our hydrogens and oxygens are balanced. So you have to balance the charge by adding electrons to the more positive side. And underline that, because that's easy to make a mistake with. All right. So this is where we actually determine one of these has to be an oxidation and one of them has to be a reduction. And this is where we actually figure that out. So let's add up all our charges here. So we'll start on this. We have 8 plus and 1 minus. So this side right here is a plus 7. So 8 plus 1s and a minus 1 is plus 7. This side here, water's not charged, so this is plus 2. So 7 plus is more positive, so I'm going to add 5 electrons. Because all I have to do is balance the charge. I don't have to make them 0. So 5 negative 1s plus 7 is plus 2, and this side's plus 2. Okay? Down here, I have minus 2 on this side. I have 0. So 0 is more positive than minus 2. So I'm going to add 2 electrons. That's going to make this side minus 2 now. And now these are balanced. So these are 2 balanced half reactions. They're both mass and charge balanced. Okay? Remember, mass and charge has to be balanced on both sides. And we sort of neglect talking about that in 130, but in reality, we are doing both. Okay? Now, you can tell which is the oxidation and which is the reduction at this time. When electrons are being added, that's a reduction reaction, when they're added as reactants, and this is the oxidation reaction. And if you went back in that previous lecture, the last reaction I wrote out was this, and I showed you that something was being oxidized and something was being reduced. All right, now we know. So, 2 more rules. When you add half reactions together, the electrons have to cancel out. So you need to multiply both half reactions by whole number integers such that the electrons cancel when they are added together. All right? So, let's think about this again. This is 2 electrons. This has 5 electrons. I need to multiply this one through by 2, and I have to multiply this one through by 5. Because 2 times 5 will give me 10 electrons, and I typically go and write above them. I write 10. 2 times this is 16. This is a 1, so now it's a 2. This is a 1, so now it's a 2. This is a 4, now it's an 8. This was a 1, now it's a 5. That's a 10, and that's a 10. I bet you can guess the last rule. You have to add the half reactions and simplify. Kind of like Hess's law. So those are our set rules. Look at them in all their glory. And then we will finish this off. So obviously my electrons cancel. That's the whole point of this. Nothing else is going to cancel because this didn't have any water or hydrogen in it. So my overall balanced half reaction, it doesn't matter the order, 16H plus 2MnO4 minus 1 plus 5C2O4 minus 2. So I'm taking care of everything on the reactant side. On the product side, I have 2Mn plus 2 plus 8 waters. Plus 10 CO2s. Now that's a mess, but that is a redox reaction that is balanced. One of the things I always go through is you're supposed to go through and make sure everything's mass and charge balanced. I kind of spot check. There's 10 carbons, there's 10 carbons, there's 2 MNs, 2 MNs, 16 hydrogens, 16 hydrogens. I always check charges. 16 plus 1, there's 10 minus 2, and then another 2 minus 2, so that's 12. So this side's plus 4 overall, and this side is plus 4 overall, because water and carbon dioxide are neutral. You have 2 of these. So this is a balanced, complete reaction. And remember, it's both mass and charge balanced. Okay? So I'm going to stop. I'm going to make one more video on balancing under basic conditions, and then a couple practice videos.